Bismillah ar-Rahman ar-Rahim. Consider the continuous time signal or function x of t. X has the set of real numbers as its domain, and the codomain is the set of complex numbers. So x of t is generally complex valued. The continuous time Fourier transform of x of t is big X of f. That's the integral of x of t times e to the minus I 2 pi ft dt. The uncertainty principle is a statement relating the width of the function x of t and the width of the function big X of f. Note that the width of a function is something that can be defined in a number of plausible ways. There is no single unique definition for the width of a function. The uncertainty principle makes use of the RMS width, the root mean squared width of a function. What is this RMS width? Suppose that we have a function g of alpha. Again, g is from R to C. G of alpha is generally complex valued. Assume that the integral from minus infinity to infinity of the magnitude squared of g of alpha is strictly positive and is a finite number. Consider the function h of alpha, which is the magnitude squared of g of alpha divided by this positive real number. H of alpha is real valued, is non-negative. We are using the magnitude squared, and the integral from minus infinity to infinity of h of alpha is, now this is just a number, so it remains as is when we do the integration, and if we integrate the numerator, we exactly get the same number that is downstairs, which means that this integral is equal to 1. So integrates to unity. H of alpha looks like the probability density function of a random variable x. A probability density function of an absolutely continuous random variable x is real valued, non-negative, and if we integrate it from minus infinity to infinity, we get unity. If we have an absolutely continuous random variable x with PDF fx of x and a finite second moment, which means that the expectation of x squared is a finite number, then this random variable has a finite first moment or a finite mean. And this mean, the expected value of x or the mean value of x is given by this integration from minus infinity to infinity of x f of x dx. Then we can compute the variance. And the variance is the integral from minus infinity to infinity. Now we take x and subtract the mean value, and then square, multiply by the PDF, and then integrate. This is the variance. This is the expectation of x minus its first moment all squared. And then we can take the square root of the variance, and that's the standard deviation. So what is the standard deviation? For a PDF associated with an absolutely continuous random variable, it gives the width of the PDF, the spread of the PDF about its mean value. So RMS width that is used in the uncertainty principle is simply this concept of standard deviation in probability. So the RMS width of x of t is equal to the square root, and then we have an integral from minus infinity to infinity, t minus t0 squared, and I will define this shortly. Then we multiply by this quantity that behaves like a PDF probability density function. And this will be the magnitude squared of x of t divided by the energy of this continuous time signal, assumed to be a positive real number, dt. And what is t0? T0 is like the first moment. So t0 is the integral from minus infinity to infinity, and then we have t times the PDF. Again, the magnitude of x of t squared divided by the energy of the continuous time signal x of t dt. So this will be the RMS width of x of t. It is a measure of width. It's not the only measure of width. As I said earlier, that there are several ways, several plausible ways of defining the width of a pulse or of a function. This is one of them, and it is the one that is employed here. Now, this can be applied in the frequency domain. So the RMS width of the Fourier transform of x of t, so that's big X of f, this will be the square root of integral from minus infinity to infinity, f minus f0 squared, the function that is like a PDF, that's the magnitude squared of x of f divided by the integral df. And what is f of 0? It is like the first moment. So this will be the integral from minus infinity to infinity f, and then we multiply by this quantity that looks like a PDF. So this is the RMS width of big X of f. a reasonable measure of the width of the continuous time Fourier transform of x of t. So what is the uncertainty principle? The uncertainty principle is that if we take the RMS width of x of t and the RMS width of its continuous time Fourier transform, and if we multiply these two guys, so the product of these two guys is greater than or equal to 1 over 4 pi. Generally, an uncertainty relation will be something that is specific to two positive quantities, to the sum or the product of two positive quantities. And the uncertainty relation is that the sum of the positive quantities or the product is greater than or equal to some strictly positive number. So the uncertainty relation here in continuous time Fourier transform is that the RMS width of the continuous time signal in the time domain times the RMS width of the Fourier transform of that signal, this product is always greater than or equal to this positive number 1 over 4 pi. So what is the meaning of the uncertainty principle? Before we proceed, what does it mean that this product is greater than 1 over 4 pi? It means that we cannot have extremely small width in time and frequency simultaneously. If both guys are very, very small, then this inequality will be violated. But this inequality, we will prove it. It must hold under some conditions. And if it holds, it means that we cannot have a continuous time signal that is very, very narrow in time, and also its continuous time Fourier transform is very, very narrow. This will be a violation of the uncertainty principle. Consequently, if we have pulses in time, if these pulses are made narrower, what will happen is that they spread. They have a larger width in frequency, and vice versa. We cannot have confinement in time and in frequency simultaneously. So this is the idea of the uncertainty principle. Let's prove it. Consider y of t. Y is from R to C. Big tau, which is just a real number. Let's examine the integral from minus infinity to infinity of t minus tau, then the first derivative with respect to time of the magnitude of y of t squared. If we use integration by parts, we get here t minus tau, and then the magnitude squared of y of t, and then we need to take the limit as t tends to minus infinity and plus infinity, minus the integral of the magnitude squared of y of t. Let's assume that the magnitude squared of y of t decays towards 0 as t tends to plus or minus infinity fast enough so that the limit as t tends to plus and minus infinity of t minus tau of magnitude squared of y of t, this is equal to 0. If this is true, then minus the integral from minus infinity to infinity of the magnitude squared of y of t is equal to this integral here, t minus tau. And now let's apply the product rule for differentiation. We know that the magnitude squared of y of t is y of t times y conjugate of t. So what I can write here is y of t dy conjugate of t dt plus y conjugate of t dy of t dt. Take the magnitude squared of both sides. So here on the left-hand side, we have the square of the energy of the continuous time signal y of t. And on the right-hand side, we have the magnitude square, and I can split this integral into two integrals. This is one, and the other one is the complex conjugate of the first one. Okay, because we have t minus tau, t and tau are real numbers, so the complex conjugate of t minus tau is t minus tau, and then we have y conjugate of t, and then the first derivative of y of t with respect to time. So this is the complex conjugate of that. Now let's use our first inequality. Our first inequality is if we have the magnitude of a complex quantity z plus its complex conjugate, then this is the magnitude of 2 times the real part of z. And the magnitude of the real part of z is less than or equal to the real part of z squared plus the imaginary part of z squared. We have equality if and only if the imaginary part of z is exactly equal to 0. So this inequality is satisfied with strict equality if z is real valued. And this square root is just the magnitude of z. So the magnitude of z plus z conjugate squared is upper bounded by 4 times the magnitude of z squared. If we apply this inequality to our problem, we get less than or equal to 4, and then we have the magnitude squared, and let's take this first by here, this integral. I will write here t minus tau y of t, and then we have dy conjugate of t dt. Now let's apply another inequality, which is the Cauchy-Schwarz inequality. So we have the inequality Cauchy-Schwarz. Now, if we have integration of f g conjugate dz, both these guys are functions of z, then the magnitude squared of this integral is upper bounded by the product of two integrals. The first one is the integral of the magnitude of f squared, and the second one is the integral of the magnitude of g squared. We have equality if and only if f is some complex number times g. We have our 4 here, and then we have the integral dt, and then we have the magnitude squared of this quantity here, that's t minus tau squared, and then the magnitude squared of y of t. And then we have another integral, and this other integral will be the magnitude squared of the first derivative of y conjugate of t with respect to t. We know, of course, that the magnitude of a complex quantity is the same as the magnitude of the complex conjugate. Now, let's apply Parseval's relation to this integral here. We have here equal to, let's copy this, 4, and then we have this integral. We will leave it as is, but then we will rewrite this integral here in the frequency domain. So what is Parseval's relation? Parseval's relation, it tells you that if we have a function, let's say z of t, and its Fourier transform is big Z of f, then the integral from minus infinity to infinity, the magnitude squared of z of t is equal to the integral from minus infinity to infinity of the magnitude squared of z of f. In other words, I can change this integral into an integral in the frequency domain. But here I need to insert the magnitude squared of the CTFT of the first derivative of y with respect to t. And what is this? From the properties of the continuous time Fourier transform, if y of t has a Fourier transform big Y of f, so that's the CTFT of y of t, then the first derivative of y of t with respect to time, it has the Fourier transform I 2 pi f y of f. Differentiation in time means that in the frequency domain, we multiply the Fourier transform of the function y of t by I 2 pi f. And if we take the magnitude squared, there is a 2 pi, and when we square this, we have 4 pi squared. With this 4, we get 16 pi squared, and then we have our first integral. And now we have this integral in the frequency domain. It will be f squared, the magnitude of y of f squared df. Let's see our current situation. Our current situation is the following inequality. On one side, we have the square of the energy of the continuous time signal or function y of t. Then we have less than or equal to, we have 16 pi squared, and then we have the product of two integrals. One of them is in the time domain, that's the integral of t minus tau all squared times the magnitude squared of y of t. And then we have another integral in the frequency domain, and this is f squared times the magnitude squared of y of f. To obtain this inequality, we have used two inequalities. One of them is that the magnitude of a complex quantity plus its complex conjugate is less than or equal to double the magnitude of the complex quantity. We have equality if this z is purely real. We also have employed the Cauchy-Schwarz inequality. And then at the last step, we apply Parseval's relation to change this integral to the frequency domain. This is our current situation. Now let's bring the function x of t into the picture. And basically, we will take x of t to be equal to y of t times e to the I 2 pi eta t, where eta is a real number. If this is the relationship between x of t and y of t, then the first observation is that the magnitude of x of t is exactly equal to the magnitude of y of t, because this complex exponential has a magnitude of unity. And so we can come here and replace this by the magnitude of x of t squared, and we can replace this by the magnitude of x of t squared. What about the Fourier transform? For the Fourier transform, y of t is equal to x of t e to the minus I 2 pi eta t. From the rules of the Fourier transform, if we take the Fourier transform of both sides, this becomes y of f, and because x of t is modulated, it's multiplied by this complex sinusoid or complex exponential, then we get translation or shift in the frequency domain. Specifically, the CTFT of x of t times e to the minus I 2 pi eta t is the CTFT of x of t, which is big X, but now it will be f plus this eta here. Let's rewrite this integral using big X. Let me use another dummy variable, u. So this is integral u squared, magnitude squared of y of u du. This is integral from minus infinity to infinity, u squared, magnitude squared of big X of u plus eta du. Now let's do change of variables. Let's have f is equal to u plus eta. So this integral is from minus infinity to infinity. Then we have f minus eta squared, magnitude squared of x of f df. What we currently have is that the square of the energy of the continuous time signal x of t, this can be written as one integral in the time domain, and then exploiting Parseval's relation, rather than having the square, I can just have the integration from minus infinity to infinity of the magnitude squared of big X of f. These two integrals are equal by Parseval's relation. This is less than or equal to 16 pi squared. Then we have an integral from minus infinity to infinity, t minus tau squared, the magnitude of small x of t squared. And then we have another integral in the frequency domain. And here we have the integrand is f minus eta squared, and then the magnitude squared of big X of f. Let's rewrite this inequality in another way. So we have the square root. We have integral from minus infinity to infinity, t minus tau squared, and then we have magnitude x of t squared, and I will divide by this guy here, dt, and I will take this integral, then x of f squared, and here I will divide by this guy here. This is greater than or equal to, moving this to the other side, 1 over 4 pi. And this is true for every tau and eta in R. Taking the infimum of both sides with respect to eta and tau, we get what are the values of tau and eta that minimizes the left-hand side. As we may expect, these are the values that act like the first moment of the random variables whose PDFs are given by these quantities here. So let's verify this. Let tau 0 be equal to the integral from minus infinity to infinity of t, the magnitude squared of x of t divided by the energy, dt. Let's show that this is minimized if tau is equal to tau 0. Let's take this integral here. And for this, I will just write PDF. And then let's subtract and add tau 0. Expand this square, so we get 3 terms. So this is one integral, which we have the square of this quantity. This is t minus tau 0 all squared. And then we get the square of tau 0 minus tau. And then we get the cross terms, and the cross terms will be 2 tau 0 minus tau, which is not a function of the dummy variable of integration. And then we have integral from minus infinity to infinity, tau minus tau 0 pdf dt. Let's look at this third term here. Now, what is this integral? This integral is equal to integral from minus infinity to infinity, t pdf dt, minus tau 0. Tau 0 and the integral of the pdf is unity. And by definition, tau 0 is equal to this integral. This means that this third term here is equal to 0. And the second term is greater than or equal to 0. Here we have a non-negative quantity, and this is also non-negative. So this integral is equal to that integral plus a non-negative quantity. For every tau in R, the integral using a general tau is greater than or equal to the integral if we use tau 0, where tau 0 is given by this integral here. And the same can be done to this second integral. So now we can write down the uncertainty relation. Now we have the uncertainty relation. The RMS width in time times the RMS width in frequency is greater than or equal to 1 over 4 pi. If we have the RMS width in frequency as the horizontal axis and the RMS width in time as the vertical axis, and then if we have this line as 1 over 4 pi times 1 over the RMS width in frequency, then it is this shaded part that is allowed by the uncertainty principle, because in this shaded part, the product of the RMS width in time and the RMS width in frequency is greater than or equal to 1 over 4 pi. This part here is prohibited. This part is where the RMS width in time and the RMS width in frequency both are simultaneously tiny, but this is prohibited by the uncertainty principle. So we can only operate in this shaded part. And perhaps in some applications, we are interested in operating using the boundary. In other words, we are interested in continuous time functions that satisfy the uncertainty principle with equality. What are those functions? now to conditions for equality. We need to track the inequalities that we have employed to derive the uncertainty principle. So in one step, we have applied the Cauchy-Schwarz inequality. There was the magnitude squared of the integral of t minus tau times y of t times the first derivative of y conjugate of t with respect to t. We applied the Cauchy-Schwarz inequality. So this is achieved by equality. So this quantity here is exactly the product of this integral of t minus tau squared times the magnitude squared of y of t and the integral, which is the magnitude squared of the first derivative. We have equality if and only if this derivative is a constant c, so c is a complex number, times this t minus tau y of t. So this is the condition for equality in the Cauchy-Schwarz inequality. This function, or one of the two functions, must be a scalar multiple of the other function. So dy of t dt is some constant c times t minus tau y of t. This condition is a differential equation. It's a famous differential equation. And its solution is that y of t is equal to some constant, let's call it gamma, and then we have exponential 1/2 this constant c times t minus tau squared. Note that we have employed another inequality, and this other inequality was that the magnitude of complex z plus z conjugate is less than or equal to 2 times the magnitude of z. And z, in our case, it was this integral from minus infinity to infinity of t minus tau y of t, the first derivative of y conjugate of t dt. This is equality if and only if z is purely real. So this means that we want this to be purely real. We want the integral from minus infinity to infinity of t minus tau. Y of t is this, so gamma e to the 1/2 c t minus tau squared. And then we have the first derivative conjugated. And so this will be c conjugate t minus tau. Y conjugate of t, that's gamma conjugate e to the 1/2 c conjugate t minus tau squared dt. So this must be real. And let's see, we have t minus tau squared, that's real. We have the magnitude of gamma squared, that's real. And then we have c conjugate. And then we have e to the power 1/2 c plus c conjugate t minus tau squared. Note that c needs to be real valued, because if c has a non-zero imaginary part, this will be a constant multiplying the integral, and we will not get a real valued z that is needed to satisfy this inequality with strict equality. So we need c to be real. C must be real valued. And so c conjugate is the same as c. Let's see where we are now. Y of t is equal to gamma. Note that there is no constraint on gamma, because in this integral, it will always be the case that gamma is multiplied by gamma conjugate. And so we get the magnitude squared of gamma, which is real valued. So gamma can be complex valued. That is not a problem. But what is needed is that c is real. What else can we say? Note that we assumed that the magnitude squared of y of t decays towards 0 as t tends to plus or minus infinity. To be specific, we assume that the limit as t tends to plus or minus infinity of t minus tau times the magnitude squared of y of t, this is equal to 0. So if c is 0, or if c is positive, actually the function y of t will explode as t tends to plus infinity, or if t tends to minus infinity. So because of this condition used in our derivation, c must be strictly negative. If beta is equal to minus 1 over 2c, and c is strictly negative, so beta is positive, now we have y of t generally takes the form gamma e to the minus beta t minus tau squared, where beta is a positive real number. Finally, the family of continuous time signals or functions x of t satisfying the uncertainty principle with equality are x of t equal to gamma. And then remember that x of t was y of t times e to the minus I2 by eta t. So e to the I2 by eta t, e to the minus beta t minus tau squared. Here, gamma is complex, non-zero. eta and tau are real numbers. They can take any value, and beta is a positive real number. So this is the family of functions that satisfies the uncertainty relation with equality. For those functions, the RMS width in time times the RMS width in frequency is exactly equal to 1 over 4 pi. We can check that the RMS width in time is 1 over 2 square root of beta, and the RMS width in frequency is square root of beta divided by 2 pi. In quantum mechanics, one form of the uncertainty principle uses the position and the momentum instead of time and frequency. So we have position x and we have momentum p. We have a function now psi that depends on x and t, but t here is just a parameter. Let's not focus on it right now. So we have psi x of t, that's the wave function in terms of x. The Fourier transform is phi of p comma t, and this is the integral from minus infinity to infinity of psi of xt e to the minus I p over h bar x dx. And we have a factor here 1 over square root 2 pi h bar. So these two functions are related via a Fourier transform relationship. And because of this, they obey an uncertainty relation. Let's rewrite this integral in the following way. Integral from minus infinity to infinity, psi of xt. Then we have e to the minus I, then 2 pi. And then we have p, the momentum, over square root 2 pi h bar. And then we have x divided by the square root of 2 pi h bar. And dx is dx over square root 2 pi h bar. So now we have phi of p prime comma t is equal to integral from minus infinity to infinity psi of x prime comma t e to the minus I 2 pi p prime x prime dx prime. And this is just the form of the continuous time Fourier transform used in deriving the uncertainty principle. And so what we have from here is that the RMS width of this function, okay, so let's call the RMS width of this function delta of x prime times the RMS width of this function, the phi function, the Fourier transform, let's denote it by delta of p prime. According to our derivation, this product is lower bounded by 1 over 4 pi. Now, if we want to write down the uncertainty principle using the actual position and momentum, then this x prime is delta x. And we just have a scaling factor, which is square root 2 pi h bar. And the same here. This is greater than 1 over 4 pi. So delta x, delta b is greater than or equal to 2 pi h bar divided by 4 pi. Then delta x, delta b is greater than or equal to h bar over 2. And that's the famous uncertainty relation in quantum mechanics. H bar is the reduced Planck constant, which is h divided by 2 pi. So here, delta x is width of psi x comma t, and delta b is width of phi b comma t, and phi b comma t is the Fourier transform of psi of x comma t. This product here is lower bounded by the reduced Planck constant divided by 2. Note that the uncertainty principle is not an issue of measurement. It is a fundamental property of quantum systems. Suppose that we have numerous identical quantum objects. They all have the same state, psi, which depends on the position. If we pick one of them and then we do a measurement of position with as high a precision as possible, then a certain value of x is obtained. If we use another object which is in the same state psi and we repeat the position measurement, then generally a different value of x will result, and so on. We will get different x values, and they will have a distribution that follows the magnitude squared of psi. And this distribution will have a mean value, and it will have a standard deviation. And this standard deviation is what we mean by the RMS width of the function psi, which depends on the position. This spread is not due to the inaccuracies of the measurement equipment. The spread of the results is a consequence of the indeterminacy of nature. This is the quantum view of nature. Its validation is not mathematical beauty or mathematical consistency or something like this. Its validation is because there are many experiments that verify the models used in quantum mechanics. If instead of the position, we measure the momentum, this will be the role of the Fourier transform of function psi, which is function phi, which depends on p, the momentum. Again, numerous identical objects, they all have the same momentum state. If we pick one of them, measure the momentum with extremely high precision, you get a value. Now, if this measurement is repeated on another of those identical objects, then a different value is obtained, and so on. There is this spread. the distribution is the magnitude of phi squared. There will be an average value, and there will be a standard deviation, which is the RMS width of function phi, which depends on the momentum. The different values that we get are not due to measurement inaccuracies. They are a consequence of the indeterminacy of nature. Now, if we have one object and we started with epsilon, then we measured the position of that quantum object, then suppose that this epsilon, due to the measurement operation, is changed to another wave function, which is epsilon tilde. Now, if afterwards we try to measure the momentum, we do have an uncertainty relation. Now, epsilon tilde, it has a Fourier transform. Its CTFT is, let's say, phi tilde. And we still have that the RMS width of epsilon tilde times the RMS width of phi tilde is greater than or equal to h bar over 2. The measurement of momentum that follows the measurement of position will be governed by the distribution, which is the magnitude squared of phi of tilde. There will be an average value, an expected value, and there will be a standard deviation.